This is Math 466, Advanced Applied Analysis, Lecture 22, I think. What I want to do today is I want to finish up the discussion of eigenvalues, eigenvectors. We may not go to the full 50 minutes, and then we will shift to now applying this on Monday to random matrix theory. So we had the triangularization lemma. And I just want to quickly sketch the proof again. It turns out the way I was doing it, it's the right way to do it. It creates a lower triangular matrix, not an upper triangular matrix. I know. So you start off with a matrix A. Any matrix A has to have an eigenvalue, eigenvector pair, right? And this is just the fundamental theme of algebra. When you look at determinant of A minus lambda, there has to be at least one root. And because there's one root, there has to be at least one eigenvector. What you then do is you form a matrix Q, which is orthogonal, and you have V1 here, and then you have Q1, 2, all the way up to Q1n. And you form an orthonormal basis. And you can do this with Gram-Schmidt. There's lots of different ways to do this. You then look at the matrix Q transpose AQ. And when you apply E1 to this, you then get Q transpose A V1, which is Q transpose lambda 1 V1. And then Q transpose of V1, well, if Q E1 is V1, then E1 is Q transpose V1. So you get back now just lambda 1 E1. So what does that mean? It means when I look at the matrix Q A Q transpose, when I apply the vector E1, which is so Q transpose A Q E1, I get back lambda 1, 0, all the way through 0. So what can the components of this look like? Oh no, maybe everything is upper triangular. Maybe I'm okay. I think I am okay. So I apply the vector 1 followed by all zeros. So this has to be lambda 1 over here, and then it has to be all zeros down here. Oh good, it is an upper triangular matrix, not a lower triangular matrix. Everything is fine. I worried myself needlessly walking in today. Because it's you don't want to deal. If you're a Star Trek fan, there's the classic episode where people are white on one half and black on the other, and then some people are black on the other one and white on the other, and they have a wonderful episode about how terrible this is. You want upper triangular, not lower triangular, so you can hang out with all the good linear algebraists. So it's got to be lambda 1 and then all zeros going down. Because I have the vector 1 and all zeros, and so when I do the dot product, what will I get? I'll get 1 times the first component, then 1 times the next, then 1 times the next, going all the way down the first column. Now, in terms of what's going on in here, I have no information. So we often put a star when we don't know what's going on. And so at the end of one iteration, I have the start of a upper triangular matrix. It's all zeros below the main diagonal in the first component. And then I have an n-1 by n-1 piece over here. And then we just do lather, rinse, repeat. We now apply the same thing here. Let's call this A2. And A2 will be an n by n matrix. And then what we can do is we can do, A2 will have, Q2 transpose. And this will give us, lambda 2, all zeros, stars here, and an A3. And then we can just bump Q2 up to a larger matrix. Q2 tilde, which would be 1, zeros like this, and then just shove Q2 in like that. And then we can have this act on the original matrix. And so at the end of the day, we get an upper triangular matrix. And so the result is, given A, there exists an orthogonal Q, A is real, such that Q transpose AQ is upper triangular. So upper triangular. Now, note, if A is real symmetric, then if we take the transpose, Q transpose AQ transpose is U transpose. Well, the transpose of this, when you take the transpose, you just do things in reverse. You'll get Q transpose A transpose Q is U transpose. Well, this is just equal to Q transpose AQ is U transpose. But that's the original matrix, so you get U equals U transpose. Therefore, U is diagonal, and in fact, U is just the matrix of eigenvalues, lambda 1 through lambda n. So it's really nice how you get that for free. The only matrix which is both upper and lower triangular is a diagonal matrix. In general, if we were doing a complex matrix, we would, instead of having a orthogonal matrix Q, we would have a unitary matrix. And we would be doing Hermitians. So we do have to be a little bit careful because we do not necessarily know that the eigenvalues are real. So in all the stuff here, I was assuming every eigenvalue was real. This is the advantage of being at the board, is we can now go back. We looked at the rotation matrices last time. The cosine theta minus sine theta, cosine theta, rotating by 45 degrees. This is a real matrix, but the eigenvalues are complex. And so when I was doing the assumption here, I don't necessarily know that lambda 1 is real. And so because I don't know lambda 1 is real, what I have to really do is I have to write U here for unitary. And I'll call this U1. And then this would be V1. And then these would become U's. And so you'll see that the proof is almost identical. And then the only thing that changes is we now take Hermitians. So we would have U1 of E1 is this. And so now we take the Hermitian conjugate. And when we apply U1 Hermitian, U1, that's just the identity matrix. So the only thing that changes is these just become U matrices. And so over here, the only thing that changes now is these are just Hermitians. So it's the same argument. So the general statement is, if the eigenvalues are not real, there exists a unitary U such that U transpose A U. Well, now I don't want to do U for upper triangular, but now since I'm not doing transposes, now I can use the letter T for triangular.
What's the definition of unitary?
Unitary is U Hermitian U equals U, U Hermitian equals the identity. So U Hermitian equals U Hermitian U equals the identity. Another way of saying this is U Hermitian is U inverse. For orthogonal matrices, it's Q transpose Q is Q, Q transpose is the identity, Q transpose is Q inverse. And so now if you go through things with complex Hermitian, you get something very similar. Yes?
Just to clarify, when we're making U1 and Q1, that's just, we're just choosing those U's and V's in order to be orthogonal?
Exactly. To be orthonormal, actually. Or to be orthonormal.
With specifically that.
So what we do is we start off with one component. We start off with one direction. And then the question is, if I give you one direction, can you complete and form an orthonormal basis? And so one way you can do this is you take your vector, then you put in the standard basis E1 through En. Now you have n plus 1 vectors. By linear dependence, you can write En in terms of all the others. So you can now throw away En. And now you apply Gram-Schmidt to your n vectors. So if you want to do it really carefully, you'd go V1, E1 dot En are linearly dependent. We can write En as a sum of alpha I, well, I'll do it this way, as alpha 1 V1 plus the sum of alpha I EI. I goes from 2 to n minus 1. And I know alpha 1 is not 0, because if alpha 1 was 0, I'd be writing En in terms of the other e's, which I know can't happen. So I can replace I don't need En. And now I have a basis, but it's not an orthonormal basis. Now we've got to be a little bit careful here. For instance, maybe V1 is equal to E2. So technically, this might not be correct. Well, I'm sorry? Well, just maybe V1 happened to be E2.
But then
how can you write
but
EN
basically
as
we
a...
can
Right, so
whichever one is.
So this is where you have to be a little bit careful. As long as we have a relationship like this, then we can get rid of En. But maybe V1 equals E2. Maybe V1 is one of those vectors. Just I'm saying, when we start the process, we have an eigenvalue eigenvector pair. Maybe the eigenvector happens to be E2 or E3 or E4.
We're not getting rid of the last one. We're getting generally rid of one.
So there's got to be one thing that's not equal to V1. V1 can't be E1, E2, E3, E4.
Yeah.
But we've got to be careful because if V1 equals E2, then it's not En we would get rid of, it's E2 we would get rid of.
That's what I'm thinking sure.
Right.
Cool.
So if V1 equals 1 is in the same direction as one of them, choose that. If not, do it like this.
But if it is equal, then your U matrix would not be n dimensions, right?
If say V1 equals E2,
Yeah.
well, I just need to write down some matrix where the first column is my V1. So I can have my first column be E2, the next column be E1. That's fine. But then I can't have the next column being E2. It's just which vector do I throw out? I wouldn't throw out En in that case. I would throw out E2. I have n plus 1 things here.
That's a special case.
It's a special case. One of these things is, at least one of them can be thrown away. The easiest way to throw away something is if it's repeated. If you have E2 twice, throw away one of the E2s. If it's not repeated, then you can have some kind of relationship like this. And if you have a relationship like this, this coefficient can't be equal to 0, because if it's equal to 0, then you've written En in terms of the others. Okay? So this is basically the proof of the triangulation lemma. So then the question becomes, why do we care about the triangulation lemma? Well, one thing is it works in under incredibly weak assumptions. I'm not assuming anything special about my matrix. Any matrix can be triangularized. If you take powers of a triangular matrix, it's still a triangular matrix. They're easy to work with. I would much rather have a diagonal matrix. All things being equal, I'd love to work with a diagonal matrix. I may not be able to get to a diagonal matrix. So I will use a upper triangular matrix because for most things, upper triangle is actually almost as good as diagonal. Also in mathematics, it's nice to work with objects that exist. If you can't diagonalize an arbitrary matrix, you can't say, well, for my matrix, I'm going to diagonalize it. Frequently, what you could do is you could say, well, if I just tweak my matrix a small amount, the probability that you're not diagonalizable is probability 0. So there is a matrix that's arbitrarily close to it. And you can sometimes try to do arguments along those lines. So here, the eigenvalue trace lemma. You may have seen this in linear algebra. The trace of A, which is the sum of I goes from 1 to n, is the sum I goes from 1 to n of the eigenvalues. How many of you have seen this in linear algebra? Oh, not the proof? Ooh, okay. Okay. How many of you have ever seen a reason why we care about this? I mean, it's like, yes?
We've been using it in statistics.
Okay.
To prove things about multivariate.
Okay, good. So it's nice to see that you're actually using it somewhere. There's a couple of different proofs. One idea is to try to look at it through the characteristic polynomial. I'm going to instead use the following. The trace of ABC is the trace of BCA. Have you seen this result, that the trace is cyclic? This is not the same as the trace of AB is the trace of BA. The trace is cyclic.
Exactly what we were using in statistics.
Excellent. So if there was homework If there was homework this week, that would be a really good homework problem. Prove the trace is cyclic. Okay? There's a limit to how much of linear algebra I want to do. It's nice to be the professor. I really don't feel like proving that, so I'm going to just leave that as an exercise. So let's look at the trace of A. This is the same as the trace of, how do I want to do this? A, Q, Q transpose. Because what's Q times Q transpose? It's the identity, right? So by putting in Q, Q transpose, I don't change anything. But this is the same as the trace of Q transpose AQ because the trace is cyclic. Okay? We all together? But now Q transpose AQ, this is a upper triangular matrix. What is the trace of an upper triangular matrix? So it's the sum of the diagonal entries. But what are the diagonal entries now for this? It's just the eigenvalues. This is going to just be the sum. I'll write it as, A. Well, I'll do it this way, I guess. Q transpose A Q I. This means just the diagonal entries. I goes from 1 to n. And that's just going to be the sum of the eigenvalues of A. And there's the eigenvalue trace lemma. So we prove it for upper triangular matrices. The triangulation lemma is really easy for upper triangular matrices because the main diagonal is just the eigenvalues.
Yeah.
And now,
true for any upper triangular matrix.
Right, well, because for an upper triangular matrix, the trace is the sum of the diagonals,
Right.
and the sum of the diagonals are the eigenvalues. And then because the trace is cyclic, the trace of A is the trace of AQ, Q transpose. It's the trace of Q transpose AQ. The next thing is a slight modification. Let's look at the trace of A to the k. This is the sum of the eigenvalues of A to the kth power. So the proof is not too bad if you look at the right way. The trace of A to the k, this is the trace of Q transpose AQ, I'm sorry, Q transpose A to the k Q because the trace is cyclic. And now what we're going to do is we're going to just do massive amounts of multiplying by 1. This is Q transpose A, I feel like Fonzie. And now between every two A's, we're going to write Q transpose Q. And so we'll get the trace of Q transpose A, Q transpose A, Q, Q transpose, I'm sorry. Q transpose A, Q, Q transpose A, Q, Q transpose A, Q, dot, 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 Q transpose A, Q. And this is now just the trace of Q transpose A, Q to the kth power. But this is an upper triangular matrix. So when you raise it to the kth power, it's still an upper triangular matrix. And the diagonals are just what you had before to the kth power. The other stuff is gobbledygook. But this is then just going to be the sum of lambda I to the k. I goes from 1 to n. And the reason for that is, oops, thank you. If I have a matrix, lambda 1, lambda n, gobbledygook, and 0. If I raise it to the kth power, it's going to become lambda 1 to the k, lambda n to the k, new gobbledygook, and 0 down there. Okay? So if there was homework, this would be another exercise. Basically, when you take the power of an upper triangular matrix, it stays upper triangular, and the diagonal is just the kth power. And so we can get the sum of the kth powers of the eigenvalues very easily. So why do we care about something like this? So the reason we care is we're going to do random matrix theory. So the way random matrix theory works is I have a matrix which is supposed to model some physical phenomena, and I want to understand the eigenvalues. We choose the elements of the matrix at random. Well, I want some formula that connects eigenvalues to matrix elements. The eigenvalues are what I want to know. The matrix elements is what I do know. And so the eigenvalue trace lemma is connecting the powers of the eigenvalues to the trace of a to the k. And it turns out the trace of a to the k will be easy to analyze. The other thing which is nice to know about this is if we go back to probability, this is looking like the kth moment. If I put a massive size 1 over n at each eigenvalue, this is the kth moment. If I understand all the moments of a distribution, I should know its density. So this is relating the moments to the matrix. Let me just write it down a little bit more explicitly. So let's say A is n by n, put a mass of size 1 over n at each lambda I. So the kth moment is 1 over n, the sum I goes from 1 to n of lambda I to the k, which from the eigenvalue trace lemma is just going to be 1 over n trace of a to the k. This is going to be a polynomial of degree k in matrix elements. So the hope is by understanding these, we will then know the moments, and by knowing the moments, we will then know the distribution. What's going to make it a little bit harder is we're going to let the matrix size grow. So it means we're going to have to understand this for all moments. But this is the rough idea of how we go about and attack these problems. All right, so there's two things I want to say, and then that will be, I think, a good place to just call it a day for the linear algebra review. The first one is not really needed for what we're doing, but it's a fact you should be aware of. So if I give you a real symmetric matrix, does anybody know an interesting fact about eigenvalues of real symmetric matrices that correspond to different eigenvalues? So A is real symmetric. Lambda 1 does not equal lambda 2. Then there's a nice relationship between V1 and V2. Does anybody remember this relationship? Has anybody seen this relationship? Anybody remember that symbol from days past? What's the symbol mean? I'm sorry? Orthogonal or perpendicular. So if you have a real symmetric matrix, if you have a different eigenvalue, you're perpendicular. So how many of you have seen this fact about real symmetric matrices? Okay. Probably. So this is nice. So I've said this many times. Boston is far, far greater than New York City. Yep. But as a Bostonian, I have to give one small part of New York City credit for being better than Boston. Which part? I'm sorry? Which roads? Where? The grid in Manhattan. Not all of them. No, I mean, in Boston, Boston, you'll have your Comm Ave and Beacon crossing as to which one is above the other one. The Boston is. Oh yeah, no. New York City, the grid in Manhattan is nice. What's nice about a grid is you have two perpendicular directions. What this is telling us is that if we have distinct eigenvalues of a real symmetric matrix, we have a basis of eigenvectors that are mutually perpendicular, so we can actually construct an orthonormal basis of eigenvectors. So the proof. Okay. So this is just a fact worth knowing. So here's the proof. Let's look at V2 transpose A V1. We know at this point that the eigenvalues and eigenvectors are real, so I don't have to worry about Hermitian. I'm going to calculate this two different ways. This is equal to A transpose V2 transpose V1, and it's equal to V2 transpose A of V1. And the reason is when I take the transpose of this, I'll get V2 transpose A transpose transpose. Well, A transpose transpose is A because it's real symmetric. What is A transpose equal to? Because it's real symmetric. It's just A. So we get A V2 A V2 transpose V1. Now we have V2 transpose, and because V1 is an eigenvector, this will be lambda 1 V1. Well, this is going to give me now lambda 2 V2. So we get lambda 2 V2 transpose V1 is lambda 1 V2 transpose V1. And because lambda 1 because lambda 1 is not equal to Lie 2, exactly. Right. So as lambda 2 does not equal lambda 1, it implies V2 transpose V1 equals 0, which implies V2 is perpendicular to V1, which is equivalent to V1 is perpendicular to V2. Okay? This is a really nice fact. One of the reasons we care about this is if I give you a matrix, let's say A is real symmetric, I can now associate often an orthonormal basis of eigenvalues. Now, if I have repeated eigenvalues, it's a little bit, you have to do a little bit more work. But let's assume the eigenvalues are distinct. So assume distinct. Then any vector v can be written as a sum of ci vi. So then if I calculate a to the m of v, this will be just the sum of ci lambda I to the m vi. So computationally, it's very fast to calculate high powers. We can actually use, assuming you have the eigenvalues. Right. But a lot of times it's pretty easy. So I'm going to use this to prove Benet's formula for the Fibonacci numbers, which we used earlier this class, using eigenvalues. So let's let Vn be Fn minus 1, where Fn plus 1 is Fn plus Fn minus 1, f of 0 is 0, f of 1 is 1. Okay? So Vn plus 1 is going to be Fn plus 1 over Fn. Well, Fn plus 1 is Fn plus Fn minus 1 over Fn. Let me see if I want to, if this is how I want to do it. Or do I want to do it the other way? This is having something coming on the bottom, which I'm not thrilled about.
I think they're okay.
When I'm trying to then write this as a matrix, well, I should be fine. All right, so this is equal to some matrix times Fn minus 1. So it's going to be 1, 1, 1, 0.
Yeah, I looked it up.
Yep. So it'll be Fn plus 1, Fn. And so when we do this, we get Vn plus 1 is AVN. Or A squared Vn minus 1. And if you notice, 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1. So if we continue, it'll go all the way down to it equals a to the n minus 1, a to the n v1. So if I want to calculate high powers of this matrix, it's not that bad. Well, what I now need to do is I need to find the eigenvalues and eigenvectors of this matrix. So every now and then it's actually nice to do a calculation and not just develop theory, but see, how would I apply it? So I want to find the eigenvalues, eigenvectors. So my matrix A is 1, 1, 1, 0. So I know the sum of the eigenvalues is the trace. It turns out the product of the eigenvalues is the determinant. So you can go about this many ways. I can look at the determinant of a minus lambda I equals 0. So I would get 1 minus lambda, 1, 1, negative lambda equals 0. So I would get 1 minus lambda times negative lambda minus 1 equals 0. So I get lambda squared minus lambda minus 1 equals 0. That should look very familiar. And you get lambda equals 1 plus or minus the square root of 5 over 2. There's the eigenvalues, there's the golden mean. Now we need to find the eigenvectors. So now we need to solve, say, 1, 1, 1, 0 equals 1 plus root 5 over 2 xy. Right? Or equivalently, if we call this the golden mean phi, we get get 1 minus phi, 1, 1, negative phi, acting on xy equals 0, 0. So now we get 1 minus phi. So the question is, what's the best way to do the algebra here? Can I multiply both sides by the inverse of this matrix?
On the first line, there should be another xy.
Ah, yes, thank you. So can I take the inverse of this matrix on both sides to solve for what xy equals? No, that's the whole point. Right? We chose phi to be an eigenvalue, so the determinant of a minus lambda I equals 0. This matrix is not invertible.
Even if it was, the other side would be 0, 0.
Right, and that would, this would tell us bad things happening. So how do I solve this? So I've got 1 minus phi of x plus y equals 0, and I've got x minus phi y equals 0. So x equals phi y, right? And now, since x equals phi y, I get 1 minus phi times phi y plus y equals 0. What values of y will work? So this becomes 1 plus phi minus phi squared times y equals 0. What value of y is going to work?
0 definitely works.
0 definitely works.
1 plus q minus q squared.
What is true about 1 plus phi minus phi squared? It equals 0. Any value of y works. This shouldn't be surprising. We have 1 degree of freedom with the vector xy. I can rescale it. So as soon as I find out that x equals phi y, I'm done. I just need to figure out what that scaling is. And so one possibility is I could take y equals 1, and then x would be phi. So one possibility is the vector phi comma 1. that won't have length 1, but that's a nice easy vector to work with. So that would be my first eigenvector. And then I would try to find the eigenvector associated to the other root. And then once I have two vectors, I can then write any vector in terms of those. And then you can use this to then sniff out a formula for the n plus first, because now we can take a high power of this matrix very easily. So I'll leave the rest of the details of this as an exercise. But this shows how you compute. This shows how you find the eigenvalues. And it really emphasizes this degree of freedom notion, that I have freedom in terms of rescaling the vector. You often scale it so that it has magnitude 1. You sometimes also scale it so that the first component is 1. So another possibility that people might use is they might use 1 for x, so then y would be 1 over phi. That's another common choice to make. When I have some freedom from here, take x equals 1. The only problem with that is it is possible that maybe x equals 0. So you might have to do that case separately. So case 1, assume x is not 0, rescale it so x equals 1, and then solve. If you can't find anything, then your assumption that x equals something non-zero is false. Take x equals 0, and then figure out what you need for y. Hopefully any value of y will work, otherwise you're in trouble. OK, any questions about this? All right, so the last thing I want to just talk about very, very briefly is the impact this has for random matrix theory. So we start off with the matrix A, and then by what we've shown we can write it as Q transpose AQ is some matrix like this, lambda, the matrix of eigenvalues, if A is real symmetric. Well, this is the same as saying A is equal to Q lambda Q transpose. And this is why I always forget which way the Q and Q transpose go, because if you look at it one way, you do Q transpose AQ. If you look at the other way, it's Q lambda Q transpose. If I give you a real symmetric matrix A, how many degrees of freedom does A have? How many entries do we need to choose?
N by n over 2.
N by n over 2.
Because
But then if you do n by n over 2, you're only counting half the diagonal. So it's n squared over 2, but you've only counted half of the diagonal. So you have to then add in another n halves. Right? For a real symmetric matrix, you choose the main diagonal, and then you choose everything above. Another way of seeing this is I choose n things for the main diagonal. How many things are left outside of the main diagonal? N squared minus n, and I take half of them. So both of those calculations will give you the number of degrees of freedom. So this is equal to n plus 1 over 2. Let's look at what's going on over here. There are n degrees of freedom from lambda, the n diagonal entries. So this tells you how many degrees of freedom you should have for Q. Right? What must this be? Well, it's got to equal n plus 1 over 2. So I think if you have n minus 1 over 2, when you then add n, that's 2n over 2. You factor out the n, and you'll get n plus 1. So the number of degrees of freedom of this orthogonal matrix Q must be n minus 1 over 2. Most of the degrees of freedom are in Q. Let's try to think about whether or not this is reasonable. So here's my matrix Q. Here's the first vector Q1. There are n components in Q1, but I claim there's really not n degrees of freedom. I claim there's n minus 1 degrees of freedom, because I can rescale the first component to be 1. With probability 1, the first component's not 0. Right? So I really have n minus 1 degrees of freedom because I can rescale that first component to be 1. And if the first component happened to be 0, then I would have n minus 1 components. So in either case, I get this n minus 1 free variables here. All right, so there's n minus 1 free variables here. Now Q2, how many free things do I have for Q2? You might think, well, it's n minus 1, because I can rescale its length. But is there any condition we must have on Q1 relative to Q2? It's orthogonal. You lose 1 degree of freedom because the dot product has to be 0. So you have n minus 2 degrees of freedom here. And if you then look at Q3, it's going to be n minus 3. So the number of degrees of freedom is n minus 1 plus n minus 2 plus n minus 3. So degrees of freedom is n minus 1 plus n minus 2, all the way down to either 1 or 0. Doesn't really matter if I stop at 1 or 0. And when you add that, that's just n minus 1 times n over 2. So in terms of a degree of freedom estimate, most of the degrees of freedoms are in the orthogonal matrix. In terms of trying to understand the physics, the Q is the least interesting part. It basically is just telling you, well, orient your system this way and the transformation will look nice. Should physics depend on how you choose your coordinate axes? I have to be extremely careful.
Yes.
It's possible that the answer is yes. I cannot prove that the universe doesn't care about how we orient our coordinate axes. There's a really good series of maps, the upside down view of the world, where they flip everything and they put the northern hemisphere in the southern hemisphere, and just, does this change how you look at countries?
It's not true. You can flip coordinates in physics.
No, it is true.
I mean, for the most part,
I hypothesized that if you weren't able to, then it would mess things up.
for the most part, the universe shouldn't care which way I choose to orient my axes,
Yeah.
right?
You
Yeah.
can't prove it.
Once you have things like quantum mechanics that, what can you observe? Again, I'm quite willing to assume that the choice of axes doesn't matter. And so when you're given a transformation, what really matters is not the representation, but the representation in that one nice basis. So another way of looking at this is there's a lot of different matrices that effectively are the same if you just change your coordinate systems. All that I really care about for matrix is the eigenvalues. The Q just tells me how I'm orienting things. I don't really care about that. So in terms of what's going on, when we study random matrix theory, we're going to care about the eigenvalues. The eigenvalues are the energy levels. And the idea is matrices are going to correspond to some physical process. And so we have like 5 minutes. So I will just end with the linear algebra approach to quantum mechanics. So quantum mechanics all comes down to solving a linear algebra problem. Some of you may have seen me lecture on this before. So these are the energy levels. And these are the energy eigenstates. Eigenstates. And H is the Hamiltonian of the system. So the only reason we can't do this in a standard linear algebra class is that there are 2 complications with H. Most of the matrices you looked at in linear algebra are finite by finite. H is infinite by infinite. So that's one problem. So one is H is infinite by infinite. And the second problem is do not know any entries of H. Other than that, it could be done in an right, and you don't know any of the entries.
Yeah, great.
So other than that, it could be done in a linear algebra class. And the expression we have in my family is, other than that, how is the play Mrs. Lincoln?
Oh my God.
So, other than that, how is the play Mrs. Lincoln? Referring to Abe Lincoln being assassinated at Ford's Theater. So this is the challenge, right? How do you make sense of a linear algebra problem with an infinite by infinite matrix where you don't know any entries? And so I will talk about Wigner's great insight, or I will give you the video to watch on Wigner's great insight, where he found a way to make sense of this in a probabilistic statistical interpretation. And this led to his getting the Nobel Prize in physics. This is Eugene Wigner. When I was a grad student at Princeton, they actually had his Nobel Prize on display in the math physics library. And so it was nice walking right by that as somebody who studies random matrix theory.